So in the previous class, we discussed the gain margin for this particular example 10 divided by s plus 1, s plus 2, s plus 3. Then I had shown you that gain margin is given by this definition, that it is the multiplication factor by which the existing gain must be increased to make the closed loop system to a closed loop marginally stable or critically stable system. So that we have already seen gain margin for this particular example is found by 1 by m. Okay, because if I multiply this particular m with 1 by m, then we will be getting unity, which means our Nyquist plot will reach the unity magnitude point, so that system will become just critically stable. Okay, so if I increase the gain beyond 1 by m, then it will enclose the unity magnitude point, which makes the system unstable because we will get n equal to 2. Once it crosses the minus 1 point after the multiplication of gain, it will enclose the minus 1 plus j0 point. Therefore, the encirclement around minus 1 will become 2. Hence, the closed loop system will become 0. So, therefore, we found out the gain margin 1 by m equal to 1 divided by 0.166, which is 6.002, and in terms of dB, it is minus 20 log m. So for stable system, I said gain margin is always positive, and it is in dB. It is positive in dB, or it is greater than 1 in magnitude. Okay, so greater than 1 in magnitude. See, you have a system. Suppose imagine you have a system which is a bike. It is stable, right? It is stable. So if gain margin is greater than 1, then only you can ride your bike faster than the existing speed. Suppose imagine you are riding your bike at say 10 kilometers per hour, k equal to 10 kilometers per hour. Then I will give you a specification saying your gain margin is 6. It means you can ride your bike at a speed which is up to 10 into 6. Okay. So 60 kilometers per hour, approximately 60 kilometers per hour is the feasible range that you can ride your bike. So when I say it, you can ride it at 60 kilometers per hour. Everyone, please concentrate. So the stable range for riding bike is 60 kilometers per hour, and you are riding at a speed of 10 kilometers per hour. Then your gain margin will be 6. Fine. But if you are riding your bike at a speed of 30 kilometers per hour, then what will be the gain margin? What is the multiplication factor that you can increase the speed of bike? Can anyone tell me the answer for this? I repeat the explanation. You are riding your bike at 10 kilometers per hour, and you still can increase 6 times greater than the existing speed. And that is bike specification. But suppose if you are riding your bike at 30 kilometers per hour, 30 kilometers per hour, then what is the multiplication factor, or how many times more than that you can increase? So I'll give the answer for this. It is 2 times, because you will reach 60 kilometers per hour if you multiply 30 kilometers by a factor of 2. 30 kilometers per hour by a factor of 2 will give you 60 kilometers per hour. So what I mean to say, there is a key point you need to understand here. So you have a system, it will always have a fixed stability gain beyond which you cannot operate. So I will give you one scooty, okay, and in the specification I will tell maximum speed is 60 kilometers per hour, okay. Then suddenly you start bike and start riding it at a speed of say 5 kilometers per hour. Okay, when you are riding constantly at 5 kilometers per hour, you have an option to increase the speed by 12 times to reach the critical stability point, which is 12 into 5 equal to 60. and slowly you will increase the speed of your bike and start riding your bike at 10 kilometers per hour constantly. So when you are riding at 10 kilometers per hour, you still have the option to increase the speed by 6 times now. Okay, so your gain margin is 6. When you increase the speed of the bike again and start riding at a constant speed of say 15 kilometers per hour. So while riding at 15 kilometers per hour, you still can increase the speed by 4 times. Getting? So gain margin is getting reduced as your speed is increasing. Okay, so you should be very cautious. You should be very cautious. So finally, after 15, if you start riding at 30 kilometers per hour, then you have only option to increase by 2 times. Increase the speed by 2 times. Fine. So beyond 2 times or beyond a factor of 2, if you increase, you have the possibility to become unstable. So and next level of speed, if you start riding at 45 kilometers per hour, you're almost trying to reach the critical stability point. So when you are riding a bike at 45 kilometers per hour, you have the option to increase the speed by 1.5 times. Sorry, 1.25 times if I'm correct. 1.33, somewhere around that. So gain margin was earlier 12 because your speed was less. Then it became 6. Then it became 4. Then it became 2. Then now it is around 1.33. And if you are riding your bike at a speed of say 59.99 kilometers per hour, so you hardly have the option of increasing the speed of the bike. So gain margin is around unity only, which means you have to stay at that point only. Okay. So this is the general notion of practical interpretation of gain margin. It is a multiplication factor. So I hope I was able to convince this. What is the actual meaning of gain margin? So keep this example in your mind whenever you come across the gain margin concept. So now we'll move on to the phase margin part. So in the previous class, I had drawn this diagram of phase margin where I wrote beta as gain margin. Sorry, yeah, beta as gain margin, and we call this particular frequency as omega g, gain crossover frequency, right? Gain crossover frequency. Let me draw the diagram once again. Just a moment. So just for the sake of understanding, I will be drawing the same diagram again. Let us consider a GH plane. So I'll write real GH, imaginary GH. Then I'll mark the minus 1 point and draw a circle now. Okay. Draw a circle which is called as unity magnitude circle. So every point on that circle will have a unit distance from the origin. Now I will draw the Nyquist plot for one typical example. Okay. One typical example where it looks something like this. And now you can see it is cutting the unity magnitude circle at particular point. Okay, at this particular point. So wherever it cuts the unity magnitude circle or unity gain circle, I will call it as gain crossover frequency or omega g. So the frequency at which it cuts the unity magnitude circle, I will call it as the gain crossover frequency. So when omega is 0, our starting point was here. When omega is increased, our points were moving like this. So when omega is moving, our points on the polar graph or Nyquist graph are moving like this. And at particular point, it will show up the magnitude of the polar plot or the Nyquist plot equal to unity. Okay, that is possible, right? Because it is moving towards the origin, so it can cut the unity magnitude circle, or it can have a unity magnitude or unity gain at a particular frequency. So that frequency I will choose it by making a simple assumption of cutting the unity magnitude circle. So that I will call as the gain crossover frequency. And in the previous class, we had also seen the point at which it cuts the 180-degree line, minus 180-degree line, as the phase crossover frequency, if you can remember. Okay, we denoted this as phase crossover frequency. Fine. So next, if suppose this plot is for say some open loop transfer function gh, okay, and if I change the location of poles and zeros for that g of s h of s, then obviously the Nyquist plot, okay, obviously the Nyquist plot will have different omega gc. Okay, suppose this is for say s plus 1 divided by s plus 2 plus s plus 3 into s plus 4, something like that, 1 divided by s plus 1, s plus 2, s plus 3. Then if I change 1 divided by s plus 5, s plus 6, s plus 7, obviously the plot will change, right? Because the phase angle is getting changed. So change in the phase angle means you may get any of these type of polar or Nyquist plot. Okay, you can get some different plots, different than the solid blue color line. Okay. So in that case, one can see that for certain GH, your Nyquist plot is enclosing minus 1 point. There is encirclement, okay, while going in this way. And for certain combination of poles, our Nyquist plot is not enclosing minus 1. Okay. So what you can observe here is omega JC is different for this combination of poles, omega JC is different for this combination of poles, as they are cutting the unity magnitude circle at a different location. So the third combination of poles is cutting unity magnitude circle here, whereas second combination of poles is cutting the unity magnitude circle here, and the first combination has cut the unity magnitude circle here. So the location of poles and zeros does matter. Okay, so for the third combination, there is an encirclement of minus 1 point, whereas first and second combination have no encirclement. Okay, so now what is phase margin? What is phase margin, we can say from these diagrams. Okay, I'm just showing the gain crossover frequencies and naming them as just omega gc dash. So for the first combination of poles, this is what we call as phase margin, because it still has an option to move the plot until beta becomes 0. So it means, say, from 0 to beta degrees is an option for the Nyquist plot, that if it moves by an angle of beta, it will just cut the unity magnitude circle at this point, or it will just touch the minus 1 plus j0 point. So the second combination has very less option, whereas third combination has something different. Okay, where there is an encirclement, it has something different. So you just look at the first and second combination, that if I change the gain, if I increase the gain, you can increase the gain, my omega PC will also move and my omega GC will also move parallel. Okay, and at certain point of gain, my Nyquist plot will just touch the minus 1 plus j0, where omega PC is also same and omega GC is also same. Okay, this is what is called a point of critical stability. So you can achieve the point of critical stability by two means. Okay, one by changing or increasing the gain, other one is by increasing the phase such that it will cut the unity magnitude circle at this particular point. Okay. So this beta, the feasible range of this beta, that is if a phase shift of beta occurs, okay, if a phase shift of this much beta occurs in the Nyquist plot, then the system will just reach the point of critical stability. Okay, therefore hence the amount of permissible phase angle such that the system will become critically stable is called phase margin. So beta is the permissible angle where the system becomes critically stable. I'll come to the practical interpretation of this. Now just listen to the theoretical aspect. Okay, from the diagram. Right? So beta is phase margin from the diagram. So the other combination is having something called beta dash. So how to calculate beta is the next discussion. So before that, I request everyone to go through this diagram just for 2-3 minutes. I said just revise that part. I'll wait for 2 minutes. And the next part is very simple, how to calculate beta. Fine. We'll proceed with the next part, calculation of phase margin. Ganesh, can you see this?
Yes, sir.
Okay, fine. So here, calculation of phase margin or beta. So I said this is one of the Nyquist plot we got. This is one unity magnitude circle, and the point at which it cuts the unity magnitude circle is called as gain crossover frequency. So we now have to evaluate beta, okay, from the diagram. Okay. So let us assume that at omega equal to omega pc, our Nyquist plot is having a phase angle of minus 150 degrees. Fine. So from here to here, approximately minus 150 degrees. So I hope everyone knows how we get this minus 150. We have done this in polar plot. So let us assume for the sake of simplicity. If you substitute omega pc some value, say around 50 radians per second, then we are getting a phase angle of minus 150 degree. So that is this point. So how to get beta then? There are two ways. Simple two ways. First one is I will subtract 180 from this angle. Okay. I will subtract 180 from this angle. So this angle is already minus 150. So this angle must be 210 degrees. Okay. So 210 minus 180 is equal to beta. Simple, very simple high school mathematics. So 210 minus 180 degrees, we'll get 30 degrees. Second way is, I'll write this expression. I don't refer the diagram, but I will write this expression, which is 180 minus 150 degree is also 30 degrees. 180 minus 150 degrees is also 30 degrees, which is nothing but 180 plus minus 150 degrees. I'll just modify this. Okay. Then we will get 180 plus, what is minus 150? It is actually the phase angle at gain crossover frequency or omega gc. So therefore I will rewrite this as 180 plus phase angle of gh j omega at gain crossover frequency omega gc, which is equal to 30 degrees. Fine. So finally, the phase margin is calculated as the universally accepted formula is phase margin equal to 180 plus gh of j omega. So how does this expression comes is by this explanation. Fine. So both ways it is correct, but this is the accepted formula where theoretically we need to solve. Then how to get omega gc, the gain crossover frequency? So it can be calculated by equating the gain equation to unity gain. Okay. So the terminology sound quite difficult. In the previous case, how we calculated omega pc is by equating the phase angle equation to minus 180 degree. You can remember that. So similarly, gain crossover frequency can be calculated by equating the gain equation to unity. So where omega gc is called as gain crossover frequency. Fine. So this is it for the phase margin. So this is it for the phase margin. So now we are done with both gain margin and phase margin discussion. Okay. So whatever numerical I have solved till this point, only those will appear in the exam, and nothing to get panic about these terminologies. I will be solving some numericals. I mean, in future classes, and Monday I will solve just one numerical. Okay, one numerical. Then I will explain it thoroughly how to calculate gain margin, phase margin for that. Then I will take all your queries. Okay. Then we will proceed with the other numericals after the internal. Okay, so please, if possible, don't miss the Monday's class. Just concentrate for one numerical so that you will get thorough familiar with all this terminology. So I explained gain margin concept with respect to a bike. Okay. Then what is actual practical interpretation of phase margin? Okay. Please remember this way of calculating beta, because all the textbooks have directly given this formula. Nobody has given how they arrived with this. So here is the explanation for that. Okay, so what is the practical interpretation of uh, phase margin? So phase margin is something related to delay. Okay, delay or phase angle difference. So if you are say asked to track one missile using your radar. Suppose imagine you have one radar. Ganesh, can you see this?
Yes, sir. Yes, sir.
Yeah, if you are asked to track a missile using something called some radar, and imagine that our missile is this one. So radar will have a huge inertia. It will be around say 2000 kgs somewhere. Okay, or some minimum means it is 100 to 150 kgs. So it will have huge inertia. But missile is a very lightweight. It can move very fast. So suppose imagine at start when it detects the first location of the missile, the radar will try to follow. Okay, try to follow the enemy missile, and enemy missile will start revolving around this radar. Okay, start revolving around this radar, and our radar will also try to rotate in the same fashion because it has to track. Fine. So at certain point of time, our enemy missile will increase its speed way at very faster rate. So earlier imagine it is making at say 500 kilometers per hour. It's making a circle at 500 kilometers per hour. and suddenly it jumps to say 5,000 kilometers per hour. Okay, it will start revolving around this radar at 5,000. So there is a huge shift, right? From 500 kilometers per hour to 5,000 kilometers per hour. Then radar will have its own limitation because of its inertia, because of its dynamics. Okay, at 5,000, it will fail to track because this inertia of the radar system cannot allow this radar to rotate at that faster rate. Okay, so it will fail to detect the actual anti-missile when the anti-missile is at revolving at a very faster rate. So how do you explain this mathematically? Okay, or conceptually is that the inertia or the dynamics of radar will not allow the delay in finding the missile and rotating the motor which is fixed to the radar. There is some what we can say like the failure in synchronization. Failure in synchronization. So that is because of the delay present delay present between detection and rotation. Detection and rotation. So when detection and rotation delay increases, then the radar system fails to track it. So if you don't have any safety precautions for the radar system, while trying to rotate to track a missile of 5,000 kilometers per hour, it will try to rotate very fastly, and finally it will collapse. Finally, it will collapse. Okay. So I hope you were able to catch something here. Okay. So there should be only finite permissible delay, or there will be only a finite permissible delay for the radar system beyond which it fails to track and it will collapse. So that permissible delay is called as phase margin. So when it is the anti-missile is revolving at 500 km per hour, your radar can track. When anti-missile is revolving at 1,000 km per hour, radar can still track by rotating around it. And when it goes to 1,500 km per hour, radar will have very small difficulty. And at 2,000 km per hour, radar is almost at critical stable point. And when your anti-missile rotates at 2,500, okay, in a hurry to catch its position, your radar will collapse because system dynamics doesn't permit that. So in that scenario, every system has a limitation, okay, limitation for a phase angle delay. Okay, phase angle delay. Another simplest example I can give is, suppose imagine you are in my control system class and I am dictating some notes for you. Okay, so at first I will dictate notes at a lower speed, which is common to everyone. So I will dictate a sentence at very slow pace. Then I will increase the speed. Then you will also increase the speed of writing. Okay. Then again I will increase speed of dictation to a higher level. Then only few will be able to, okay, write my dictated sentences. Some people will fail because they cannot catch my speed because their delay in writing and listening is has crossed their phase margin. Okay, and finally I will dictate the sentence such a way that nobody can copy the notes. It means the delay in dictation and writing has been crossed. Has been crossed. Therefore, the permissible phase delay has been crossed. So that's what the phase margin concept means. Okay, so mathematically it is given by this formula. This formula 180 plus gh of j omega and the phase angle at omega g. So are you able to understand the practical meaning of phase margin?
Yes, sir.
Okay. So Aditya Bhaskaran,
Yes, sir.
yes. So in general, phase margin is the permissible delay between input and output. What is the maximum phase angle difference for an RC circuit? For an RC circuit? Okay, leave for RC. What is the maximum permissible phase angle delay for a pure capacitance circuit? Phase angle difference. It is plus 90 degrees, right? Because output leads, input lags. Similarly, for an inductor, what you can say? The maximum permissible phase angle difference for a pure inductor, it is 90 degrees. the output can lag only by 90 degrees. Okay, that is a permissible delay. So beyond 90 degrees, what happens? Nobody has exploded, but that is the permissible delay. So similarly, like they are like a capacitor or a inductor, even RLC circuit have some limitation. Okay. So one more question, in general question, you can think about it later. When a system will actually fail to track the input, is it at lower frequencies or is it at a higher frequencies? When a system fails to track the input, is it at low frequency input or is it at high frequency input? So think on this and you can get an answer for phase match. I mean, you can still interpret in depth about the phase match. So that's about today's class, and we'll continue with more discussion in the next class. And I will solve one simplest numerical, and the syllabus I have already sent. I already sent. Just understand the concept and practice few numericals. That will be sufficient for the internals. Any queries?
So for the polar plot, for the
Yeah.
internals, if it's any numerical, should we use a graph sheet?
If you use a graph sheet, that is better.
Okay, sir.
Okay, so polar plot, and if there is any like magnitude, high magnitude at omega equal to 0, then no exact scale is required. No exact scale is required, but just the shape is sufficient.
Okay, sir.
Okay, I hope that is sufficient for the internals, and do well and all the best. Okay, so concentrate more on numericals. More on numericals. I mean, whatever is solved in the class, if you can go through it thoroughly, that is sufficient. Okay, fine then. Thank you and bye.